Welcome back, Logan. You made it. It's the end of the week. Hope you guys are ready for another installment of Math from Your Couch. Today, what we're going to do is we're going to take a look at the chords and we're going to dissect the last property of congruent chords. And what this last property says is that two chords in the same circle, kind of like chord NM and HJ, these two chords are congruent to each other if and only if they are equidistant to the center. So these chords are going to be congruent if the distance they are to the center is exactly the same. Now the same thing can be stated in its converse fashion. What that means is if these two chords are the same distance to the center, then they must be congruent. So if they're congruent, their distance to the center must be the same. And you could also say is that if their distance to the center is the same, then they must be congruent. So this is what the theorem looks like, or the property looks like written out. Two chords in the same circle are congruent if and only if they are equidistant to the center. You notice I left out that blue part right there. That just means if you had two circles that were exactly the same as well. And then you could look at the chords that way. All right, so let's break this down. What I want to say is if I want to know how far two chords are from the center, I need to draw some radii. So I'm going to draw two pieces of radii that are perpendicular to those chords. That perpendicular part is essential. If the radii are not perpendicular, if you don't draw perpendicular radii, then what's going to happen is this theorem doesn't work, because that's the definition of distance from a line to a point. So we want to start off with having two radii that are perpendicular to those chords. Second, if these two radii, are congruent to each other, so if the two pieces of radii that are perpendicular to the chords are congruent to each other, then you can now say that the chords must be congruent to each other, and vice versa. So if the chords are congruent, then the radii that are perpendicular to those chords must also be congruent to each other. This right here, this radii, represents the distance that the green line, the green segment, is to the center. Okay. All right, so let's take a look at an example. Now this first example, what we're going to do is we're going to kind of dissect what's going on here and get a little bit better understanding of what's going on. So what we have here is we have three chords. We have chord AB, chord HI, and chord XY. And of these three chords, you also have three pieces of radii that extend to them and are perpendicular to them. Now when you look a little bit further, let's give them some numbers. What we have is we have that the chord AB is 8 units away from the center, and chord HI is 6 units from the center, while chord XY is 7 units from the center. So you notice real quickly that chord AB is farther from the center than chord HI is. Now here's a byproduct of this theorem we just looked at. If this chord is further away, that means it's being pushed further into the circle. And as you're being pushed further into the circle, your distance or your length of your chord must be smaller, because you're going to have less diameter, less width of the circle to expand. Whereas this chord is much closer to the center of the circle, which means it must be longer in length. You'll notice that none of them are congruent to each other, right? So none of these chords are the same distance to the center, which means none of these chords can be congruent to each other. Okay, let's take this example and let's give it an actual math reference that you might see in your homework. So we have this new problem, same exact picture, except this time the chords are different. The radii are different lengths. So AB is 23 units from the center. Chord HI is 23 units from the center, and chord XY is 25 units from the center. You'll notice that chord XY is much further away, which means XY is probably going to be the smaller one. Not probably, will be the smaller one. So XY is going to have shorter length. Now these two chords over here, okay, chord HI and chord AB, have the same exact distance from the center, which means they must be congruent using that property we talked about just a couple of minutes ago. All right, here's the question. What is the value of x given that AB is 3x plus 10, HI is 7x minus 2, and XY is 10x minus 16? All right, so it looks like we have to make an equation. So what we want to do is we want to take a look at the picture and make sure that we understand the implications of what's going on here. So since this radius, this piece of the radius is congruent to this piece of the radius, then that tells me that these chords HI and AB must be congruent. And this is my equation. So I'm going to set up that chord AB, the 3x plus 10, must be equal to the chord HI, which is 7x minus 2. So these two things have to be equal. Once you have that set up, your geometry is pretty much done. Now it's just algebra 1. You're going to go ahead and solve this by subtracting the 7x from both sides and then isolating the variable x by subtracting 10 and then dividing both sides by -4. All right, so this gives an answer of x equals 3. All right, let's move on to the next problem, our last example. Now, this example is one of my favorites. This example here requires a little bit more creativity when trying to solve it. So what we have is we have two chords. We have chord HJ and chord QR. Our job is to find out how long QR is. Now what I noticed very quickly in this problem is that the length or the distance that HJ is to the center A and the distance that QR is to the center A is exactly the same. Now because the centers are exactly the same, okay, so I'll go and mark that up, because the chords, not the center, sorry, because the chords are exactly the same distance to the center, what I can do is I can conclude that the chords themselves must be congruent. So if the chords are the same length to the same distance to the center, then those chords are congruent to each other. Now, if that's true, what I now know is that these two pieces, right? So these yellow-green pieces here and these yellow-green pieces here are going to be exactly the same. So it doesn't matter if I solve up here for QR or if I solve down here for HJ. Solving for either of them will give me the same exact answer. So what I'm going to do is I'm going to use the one that has the most amount of information. So on this one, you'll notice that you have, green, yellow, and some red. And over here you have green, yellow, red, except on this one, in this cross section, in this T section, you'll notice not only do you have just the 6, but you also have the 4. If you want, you can move the 4 up there, or you can just work with this location and solve this. And that's what I'm going to do. So I can solve either of them because they're exactly the same, but I'm going to choose to solve this one, right, the one with HJ, because it has more information. Now when I look at this, this is absolutely useless to me. So this is what I want to do, is I need to come up with a strategy to solve a problem that looks like this. So anytime you have a T section, right, so anytime you have a T section inside of a circle like this, one trick, one thing you can do is you can draw a second radius. Now you might be asking why I would want to draw a second radius, and it's because I know the entire length of my radius. Since AG is a radius and AG is 6 plus 4, then I know that the radius in this picture is 10. Every single radius in this picture is 10. So if I was to draw another radius, it would also be 10, and that's exactly what I'm going to do. I'm going to draw the radius from A to J. Now some people might ask why I did that, and it's because it creates a right triangle. And that's the creativity that's needed to solve this problem. We have to be able to construct a second line, a second radius that helps us solve it. So anytime you get one of these T sections like this, just think, okay, is drawing another radius going to be helpful? Do I know what that radius is, or should I know what that radius is? So what we're going to do is we're going to draw that radius, and then I'm going to pop that triangle out right there, and now I'm going to just label it. So I know that the green segment is going to be 6 because it says so, and the purple segment, which is the radius, is going to be 10. I need to solve for x. So I'm going to set up my Pythagorean theorem. So I set up Pythagorean theorem. 6 to the power of 2 plus x to the power of 2 is equal to 10 to the power of 2. Now I'm going to go ahead and solve this, and I get x is equal to 8. So what that tells me is that this x is going to be 8, and so will this piece over here. So those are both going to be 8. So I now know that those are both 8. But if you remember from yesterday's video, if a piece of the radius is perpendicular to the chord, then the chord is being cut perfectly in half, which means I now know that from H to K will match what K to J is. So this piece must be 8. So I'm going to say that this is 8. But remember, these two chords are congruent to each other. So they're all going to be 8 for their pieces. Now this is going to lead me to my final answer. Since I know that the piece from Q to P is 8 and P to R is 8, I can now conclude that Q to R is 16. And this is our answer. QR is equal to 16. All right, so if you had any trouble with any of these problems, what you're going to want to do is go back, rewind the video, and go to that portion of that video. Go to that problem and watch it one more time. If you need to slow it down, then just change the speed on it. And if you have any questions, come by office hours today or class, and I'll try to address them, or you can email me. If anything doesn't make sense, please contact me as soon as possible. All right, I hope you guys have a great weekend, and I'll talk to you on Monday.